Hello, students! Have you ever wondered why catching a very fast cricket ball stings your hands? Or how a huge rocket is able to launch itself into space? Well, these are some of the questions we will be answering today as we explore Sir Isaac Newton's famous laws of motion. We are going to see how these laws are working all around us, in everything we do, from simply walking to driving a car.
So are you ready to begin? Here is what we have planned for our lesson today. First, we will start with the concepts of force and momentum. Then we will learn how we can soften the blow of an impact. After that, we will explore the very interesting world of Newton's third law and see it in action. And finally, we'll wrap it all up with a summary of why all these concepts are so important for you to understand.
Right. Let us start with that first question I asked. Why does a fast cricket ball sting so much when you catch it? To find the answer, we first need to understand three things: force, momentum, and impact. So let's dive into our first section and look at this very common experience. I want you to really think about this. A fast cricket ball can really hurt your hands. But if the ball is moving slowly, it doesn't hurt so much. Why is that? The answer you see is in a concept called momentum. Momentum is, well, you can think of it as a measure of how difficult it is to stop a moving object. The more momentum something has, the harder it is to stop. Yes, it is all about momentum. As you can see here, momentum, which we represent with the letter P, is calculated by multiplying an object's mass by its velocity. So something can have a large momentum if it has a large mass, or a large velocity, or both. To stop any moving object, you have to apply a force to change its momentum down to zero. So, we now know that a fast cricket ball has a lot of momentum. The question is, how can we catch it without getting hurt? That is exactly what we are going to explore in our next section, softening the blow. We'll learn a very clever trick that good cricket fielders use, and it is all based on physics. Now, this brings us to a very key idea from Newton's second law of motion. It tells us that force is the rate at which momentum changes. What does that mean? It means it's not just about how much the momentum changes, but also about how quickly it changes. If you try to stop that cricket ball instantly, in a very short time, you will feel a very large force on your hands, and that is what causes the sting. So, how do professional cricketers do it? How do they catch such fast balls without injuring their hands? Well, it's all about increasing the time of impact. A good fielder will move their hands backward as they catch the ball. This simple action, as you can see in steps 3 and 4, increases the amount of time it takes for the ball's momentum to become zero. And that is the secret. It is a very important relationship. By increasing the time of impact, the fielder greatly reduces the force of the impact on their hands. It's an inverse relationship, you see. More time means less force. This is a beautiful and very practical application of physics that you can see in sports. And this principle of increasing the time of impact is not just for sports, it's a key idea in safety engineering. Think about it. A high jumper lands on a thick, cushioned bed to increase their stopping time and reduce the force on their body. In a car, seatbelts and airbags are designed to do the very same thing during a collision. They slow you down over a longer period of time to reduce the force and prevent serious injury. Now, let's move on to another very interesting topic. Have you ever wondered how a rocket can travel in the emptiness of space where there is nothing to push against? Or how a simple bird is able to fly? The answer to all this lies in another of Newton's brilliant ideas, the third law of motion. This law is all about pairs of forces, and it's one of the most fundamental rules in all of physics. Here it is, the famous law. To every action, there is an equal and opposite reaction. It is a very simple sentence, but its meaning is very deep. You can think of it like this. You cannot touch anything without it touching you back. If you push on a wall, the wall pushes back on you with the exact same force. It is a universal rule. This table here helps us understand these action-reaction pairs a little better. You see, they are always equal in size or magnitude, and they are always in opposite directions. But here is the most important point, and I want you all to remember this. They always act on two different objects. The action force is on one body, and the reaction force is on another body. This is a very crucial point. Okay, so we know that these action-reaction pairs are everywhere. But what do they actually look like in our daily lives? Let's look at some simple examples to make this idea even more clear. You might be surprised to see how often you use the third law without even realizing it. Let's start with something we do every single day: walking. When you walk, what do? You push the ground backward with your foot. That is the action. Now, according to Newton's third law, there must be a reaction. And what is that reaction? The ground pushes your foot forward with an equal and opposite force. It is this reaction force from the ground that actually moves you forward. Here is another example, a gun being fired. When a gun is fired, it pushes the bullet forward with a very large force. That is the action. At the very same time, the bullet pushes the gun backward with an equal and opposite force. That is the reaction. And this backward push is what we feel as the recoil or the kick of the gun. Have you ever tried to jump from a small boat onto the shore? It can be tricky. This is another classic example of Newton's third law. To jump forward, the sailor has to push the boat backward with their feet. That is the action. The reaction is that the boat pushes the sailor forward, helping them reach the shore. But what also happens? The boat itself moves backward, pushed away by the sailor's feet. Now, this leads us to a very important question. It's a question that confuses many students. If the action and reaction forces are equal, and they are opposite, why don't they just cancel each other out? Why does anything move at all? It's a very good question, and the answer is actually quite simple. And here is the answer. Please pay close attention. The forces do not cancel out because they are acting on two different bodies. Remember the gun and the bullet? The action force from the gun acts on the bullet. The reaction force from the bullet acts on the gun. Forces can only cancel out if they act on the same body. A force on the gun cannot cancel a force on the bullet. They are separate. But you might be thinking, the bullet flies off with a very high speed, but the gun only kicks back a little bit. How can this happen if the forces are equal? Well, for this, we must remember Newton's second law, F equals ma. Even though the forces are equal, the masses of the gun and the bullet are very, very different. The gun has a much larger mass, so it has a much smaller acceleration. The bullet has a very small mass, so that same force gives it a huge acceleration. So, we have seen how Newton's laws of motion are working all around us in so many different situations. Now let's just take a moment to wrap things up and review the most important points from our lesson today. These are the key ideas you will want to remember, not just for your exams, but for understanding the world. All right, let's summarize. First, to reduce the force of an impact, you must increase the time over which the impact occurs. Second, forces in our universe always come in pairs, action and reaction. Third, these action and reaction forces are always equal in magnitude and opposite in direction. And finally, the most important point to remember, they act on different objects, and therefore they do not cancel each other out. And now, I have a small challenge for you. As you go about the rest of your day, I want you to look around and try to find examples of Newton's third law in action. Can you spot 3? It could be a bird flying, someone swimming, or even just the simple act of you sitting on a chair. The world is like a big physics laboratory. So go on and explore. What will you discover today?